Oxidation reactions of monosaccharides. A number of oxidizing agents are used to identify functional groups of carbohydrates. The most important are Benedict's or Tollens reagent, bromine water, nitric acid, and periodic acid. Benedict's reagent. Benedict's reagent is a chemical reagent named after American chemist Stanley Rochester Benedict. It is a complex mixture of sodium carbonate, sodium citrate, and copper 2 sulfate pentahydrate. This is the structure of citric acid. If you replace one hydrogen or one proton here by sodium plus, you will get monosodium citrate. And if you replace 3 hydrogens, this 1, 2 and 3, then you will get trisodium citrate. The principle of Benedict's test is that when reducing sugars are heated in the presence of an alkali, they are converted to powerful reducing species known as indiols. Indiols reduce the cupric compounds present in the Benedict's reagent to cuprous compounds, which are precipitated as insoluble red copper 1 oxide. So in case of Benedict's solution, Cu2 plus, which is a cupric complex, is present, and it reacts with the aldehyde group, and aldehyde or this keto group is converted and oxidized. Then we get oxidation products, and this copper 2 plus is reduced to copper 1 oxide. So in case of aldoses, if you take beta D glucopyranose, the open chain form of this D-glucose will react with the Benedict solution, and this CHO group will be oxidized into carboxylic acid group. As the medium is basic, this will remain as carboxylate ion, and you will get a gluconic acid salt. Now in case of alpha hydroxyketose, this is the structure of alpha hydroxyketose. What is the alpha hydroxy? The alpha hydroxy means this ketone, and this is the alpha carbon. The alpha carbon of this ketone contains an OH, an hydroxyl group. This is called alpha hydroxyketone. If you add Benedict solution, as it is basic, this alpha hydroxyketone will remain in the indiol intermediate form, and this will further react with the base to give aldehyde or an aldose. Now if you add the Benedict solution or the copper 2 plus ion, then this aldehyde will be converted into carboxylate ion, and the copper 2 plus complex will be reduced to this Cu2O, copper 1 oxide. If you take beta D fructopyranose, then this is the shear form. In medium, this will remain in the equilibrium with the open shear form, and this open shear form will remain in the equilibrium with glucose and mannose. You all know that in the basic medium, glucose, fructose and mannose, they are interconvertible. Thus now if you add the Benedict solution, you will get this gluconic or mannonic acid salt and a brick red precipitate of copper 1 oxide. Preparation of Benedict's reagent. At first, dissolve 173 gram of sodium citrate and 100 gram of anhydrous sodium carbonate in 800 ml of slightly warm distilled water. Filter it if necessary. Then dissolve 17.3 gram of copper sulfate in 100 ml of distilled water separately. So in one pot you are doing this, in another pot you are doing this. Then you are adding these two mixtures. So mix this copper sulfate solution slowly with 800 ml solution mixture with constant stirring. Now make the final volume 1 liter, that means 1000 ml, with distilled water. Now this is an experiment if to understand whether you have an aldose or ketose. If you put the substance in water and then add 3 ml of Benedict solution, and you have to then boil for few minutes. If you observe that a red, green or yellow precipitate is appearing, then you have to be confirmed that the reducing sugar is present there. And if the solution remains clear or just a little blue color appears, then you have to be confirmed that reducing sugar is not present there. Benedict's reagent can be used to test for the presence of glucose in urine. Glucose in urine is called glucosuria and can be indicative of diabetes mellitus. But the test is not recommended for the diagnosis of diabetes mellitus, because in case of urine there are a number of other things are present in urine, so that's why it can give any false test. That means maybe glucose is not present, but still you are getting a positive test with the Benedict solution. That's why this method is not done in practical use. Tollens reagent. Tollens reagent is a chemical reagent used to determine the presence of aldehyde, aromatic aldehyde, and alpha hydroxyketone functional groups. The reagent consists of a solution of silver nitrate and ammonia. It was named after its discoverer, the German chemist Bernhard Tollens. Tollens reagent can be used to distinguish ketone and aldehyde. Tollens reagent gives a negative test for most ketones, with alpha hydroxyketones being one exception. That means in case of aldehyde and alpha hydroxyketones, this Tollens reagent will give a positive test. Now see, if you take an aldehyde and add some Tollens reagent, then you will get a carboxylic acid and a silver mirror, by which you can determine that this substance is giving a positive test. You can see this silver mirror. Preparation of Tollens reagent. First, a few drops of dilute sodium hydroxide are added to some aqueous silver nitrate. The OH, that means the hydroxyl ions, convert the silver aqua complex into silver oxide Ag2O, which precipitate from the solution as a brown solid. That means you have this silver nitrate and you are adding some sodium hydroxide. Then you will get this silver oxide, which will just precipitate from the solution. In the next step, sufficient aqueous ammonia is added to dissolve the brown silver oxide. The resulting solution contains the silver amine complex AgNH3 in the mixture, which is the main component of Tollens reagent. Sodium hydroxide is reformed. So at first stage, this one is occurring, this reaction, and in the next stage, when you are adding much more ammonia, ammonia is reacting with this silver oxide, and there is a silver amine complex. This complex is being formed. Alternatively, aqueous ammonia can be added directly to silver nitrate solution. At first, ammonia will induce formation of solid silver oxide, but with additional ammonia, this solid precipitate dissolves to give a clear solution of diamine silver complex. Filtering the reagent before use helps to prevent false positive results. In a positive test, the diamine silver complex oxidizes the aldehyde to a carboxylate ion, and in the process is reduced to elemental silver and aqueous ammonia. The elemental silver precipitates out of the solution, occasionally onto the inner surface of the reaction vessel, giving a characteristic silver mirror. And this is the oxidation process of alpha hydroxy ketones. You are taking alpha hydroxy ketone, the basic medium, so you are getting indiol intermediate, and this is converting into aldehyde or an aldose, and then this silver amine complex is coming to this aldehyde, and this carboxylic acid salt is being prepared, and you are getting a silver mirror by which you can confirm the presence of this aldehyde or alpha hydroxyketose group. Tollens reagent can also be used to test for terminal alkynes. A white precipitate of the acetylide is formed in this case. Okay, in case of terminal alkyne, if this is present in your reaction mixture, then it can give some false test. Let me show you. Terminal alkyne means this one, R, C triple bond C H. If the Tollens reagent reacts with this, then this will form this one, R C triple bond C Ag, silver acetylide, and you will get, in case of this, you will get a false test. Reducing and non-reducing sugars. Sugars that give positive tests with Tollens or Benedict solution are known as reducing sugars, and all carbohydrates that contain a hemiacetal group give positive test. In aqueous solution, the hemiacetal form of sugars exist in equilibrium with relatively small but not insignificant concentrations of non-cyclic aldehydes or alpha hydroxy ketones. These two undergo the oxidation, perturbing the equilibrium to produce more aldehyde or alpha hydroxy ketone, which then undergoes oxidation until one reactant is exhausted. This is the structure of reducing sugar, where one group will be OH and another is OR. That means this is the hemiacetal form. This one is OH and this one is the OR linkage. And in case of acetal form, this is the cyclic structure. This one is the complete cycle. So this is the OR connectivity, and this one is also OR. That's why this is the acetal form, which is non-reducing sugar. Carbohydrates that contain only acetal groups give negative taste with Benedict's or Tollens solution, and they are called non-reducing sugars, as acetals do not exist in equilibrium with aldehydes or alpha hydroxy ketones in the basic media of the test reagents. So this is the example of some reducing sugar and non-reducing sugar. beta D glucopyranose and beta D fructopyranose are the examples of reducing sugar, because you can see, just if you look this carbon, this is attached with one OH and another OR group, so this is a hemiacetal form. Similarly, this carbon is also a hemiacetal. Oh, where is it? This carbon. No, actually not this one. Actually, it should be, sorry, this one. This one is the hemiacetal linkage, where this carbon is attached with one OH and another one OR. And in case of methyl beta D glucopyranoside or ethyl alpha D fructofuranoside, these two are non-reducing sugar, because this is also OR, this is also OR, so this is the acetal form, and here also this is the acetal form. In case of this carbon is attached with this OR and another one is attached with this OR. Bromine water oxidation. Bromine water is a reagent that selectively oxidizes the CHO group, that means the aldehyde group, to a carboxylic acid group, thus converting an aldose to an aldonic acid. So if you take an aldose and add bromine water, then you will get aldonic acid. Because the alkaline conditions of the Tollens test also promote the equilibration of aldoses and ketoses, ketoses also give positive Tollens test. Glycosides are not oxidized by bromine water, because the aldehyde carbonyl group is protected as an acetal. Thus, bromine water cannot oxidize ketones and glycosides. So, if you want to distinguish between the aldoses and ketoses, so you have to use this bromine water. Aldonic acids exist in acidic solution as lactones, called aldonolactones. The lactones with 5-membered rings are somewhat more stable than those with 6-membered rings. So, this is the D-glucono-delta lactone. This is the beta D-glucopyranose structure, and you are adding bromine water. So this OH group will be oxidized into this C-double-bond-O group. Now this is the structure of lactone, OCO. This is a lactone. Now how to give a name? If this one is your carbonyl group, this carbon is the alpha carbon, this one is the beta, this one is the gamma, and this one is the delta. Now this O group, this oxygen group, is connected with the 4th carbon, that means in the delta carbon. That's why this is a delta lactone. So I hope you can understand how to do the nomenclature. Alpha, beta, gamma, and this one is the delta. Experiments with aldopyranoses have shown that the actual course of the reaction is somewhat more complex than it has been indicated. Bromine water specifically oxidizes the beta anomer, and the initial product that forms is a delta aldonolactone. This compound may then hydrolyze to an aldonic acid, and the aldonic acid may undergo a subsequent ring closure to form a gamma aldonolactone. So what is the course of the reaction? You have this D-gluconic acid. Oh no, not this one. Actually, start with this. Oh, I'm confused actually. You have got this delta lactone here, and now if you add some water, then you will get this gluconic acid. Now after this, in case of delta, this OH was in the ring formation. This OH was involved in the ring formation. But after adding water, you have got this gluconic acid. Now this OH can also make the ring, a 5-member ring. So this will be a gamma gluconolactone. You know the nomenclature. Again, this one is alpha, this one is the beta, this one is the gamma. So this oxygen is connected with the gamma carbon. That's why this will be the gamma gluconolactone. This is the structure. Okay, this is the entire course of this oxidation. First you take this beta D glucopyranose, then add bromine water, then this OH will be converted into C double bond O. That means a lactone will form. As this oxygen is connected with the delta carbon, so you are getting a delta lactone. Then add some water, you will get a gluconic acid, and this gluconic acid will be in equilibrium with this gamma lactone. This OH is attacking here and forming this cyclic structure, which is a D-gluconic gamma lactone. Now see the detailed mechanism of oxidation. You have bromine water. That means this bromine water means HOBr plus HBr. You know bromine can just break. Bromine, this, if you take this Br2, if you take this Br2, so after this heterolytic cleavage, one will become Br minus, another one become Br plus. So the Br minus will take a proton and form HBr, and the Br plus will form HOBr, where Br is plus here, this Br is plus, this Br is plus and OH is minus, and here this Br is in minus oxidation state. So after this oxygen will take up another proton and this will form this. Now this carbonyl group, this oxygen can attack this Br, this one, because this has become a good living group. So now just follow the reaction mechanism. At first water is attacking this carbon, and simultaneously this lone pair of oxygen is attacking this Br. So you are getting this structure. After the deprotonation you will get this, and now this hydrogen will leave becoming HBr. This hydrogen and this bromine will leave, so you will get this aldonic acid. Similarly, just look at the beta D glucopyranose, the chair form. This oxygen will attack this bromine, which comes from this HOBr, and then this hydrogen will leave being HBr, and then you will get D-gluconodelta lactone. Now beta D glucopyranose undergoes oxidation by bromine water 250 times faster than alpha D glucopyranose. Now see what is the case. This is the beta D glucopyranose, which can oxidize faster than this alpha D glucopyranose. Why so? Because in case of beta D glucopyranose, this H and this Br are anti-periplanar. That's why the E2 reaction, the elimination reaction, occurs much more easily. So you are getting D-gluconodelta lactone. But in case of alpha D glucopyranose, when you treat it with bromine water, then if this H is here, because the hydrogen is in equatorial position, you have to keep this bromine here so that it can become anti-periplanar. But this bromine feels some repulsion with these hydrogens, the hydrogen of this 3 and 5 carbon. This is also said 1,3 diaxial strain. So because of this repulsion, this bromine cannot be in the anti-periplanar arrangement. So this bromine adopts this syn periplanar arrangement, and which doesn't readily gives the E2 reaction. That's why this alpha D glucopyranose is very much slower in case of the oxidation than the beta D glucopyranose. Now just read it. In case of beta anomer, CH and OBr bonds are anti-periplanar to each other, or the anti-parallel to each other. The stereoelectronic requirement for an E2 reaction is the anti-periplanar arrangement of the departing groups. Also, the elimination of a proton from the axial position is more favorable than from an equatorial position. In alpha anomer, the axial hydrogen atoms at C3 and C5 hinder the anti-periplanar arrangement of CH and OBr bonds, and actually it takes up a syn periplanar conformation, from which elimination of HBr does not take place. The very slow rate of the oxidation of alpha anomer is due to its conversion to the beta anomer, and then it follows the oxidation. So the alpha anomer first converts into the beta anomer, and then it is oxidized. Nitric acid oxidation. Dilute nitric acid is a stronger oxidizing agent than bromine water, and it oxidizes both the CHO, that means the aldehyde group, and the terminal CH2OH group of an aldose to this carboxylic group, and it forms a dicarboxylic acid which are known as aldaric acid. So this is your aldose, this is the aldehyde group, and this is the terminal CH2OH group. If you take nitric acid, both of this group will be oxidized into COOH, and you will get aldaric acid. The aldaric acid obtained from D-glucose is called D-glucuric acid. So this is the structure of your D-glucose. This is the open chain structure, and if you treat it with nitric acid, this one will be oxidized. Similarly, this one will also be oxidized, and you will get D-glucuric acid. Now this D-glucuric acid, what happens? This can form 3 types of lactone. This is the D-glucuric acid 3,6 lactone. This number 3 OH group is attacking this 6 number of carbonyl or COOH group. So this type of lactone is being formed. In another case, this 4 group can attack this 1 carbon. So you can get a 1,4 lactone. And in another case, both of this one and this one can occur simultaneously. That means this 3 hydroxyl group can attack this 6th position of the carbonyl group, and this 4th hydroxyl group can attack this 1 number of carbon. So you will get this structure 1,4,3,6 dilactone. Now, mechanism of oxidation. Just understand it properly. This is the form of nitric acid, which we say HNO3. Actually, this is not neutral. That means we say that this is neutral HNO3, but the positive charge and negative charge center are not in the same place. This nitrogen remains in plus charge and this oxygen remains in the minus charge. Now this OH takes up a proton and this is becoming OH2 plus, which is a very good leaving group. So after the elimination of water, this nitrogen gets another one plus charge. This is actually NO2 plus. We say this NO2 plus. In the actual, this nitrogen is possessing 2 plus charge and this oxygen is possessing 1 minus charge. So the overall charge will be 1 plus charge, which is NO2 plus. And now if you have this alcohol, this oxygen can attack this nitrogen. So you will get this moiety. And after that, after the elimination of HNO2, this hydrogen will take up this whole group. And after the elimination of this HNO2 or HNO3, you will get the aldehyde. And then again another molecule of nitric acid will come and this one will attack this aldehyde group. So ultimately you will get a carboxylic acid. This is the mechanism of the nitric acid oxidation. Per-iodate oxidations. Oxidative cleavage of polyhydroxy compounds. Compounds that have hydroxyl groups on adjacent carbons, that means vicinal diol, undergo oxidative cleavage when they are treated with aqueous per-iodic acid. The reaction breaks carbon-carbon bonds and produces carbonyl compounds. This is the stoichiometry of oxidative cleavage by per-iodic acid. You have this carbon-carbon bond and this vicinal diol. You are treating it with HiO4, then this bond will be broken and you will get two molecules of ketones in case of this, and HiO3 plus H2O, etc, etc. And what is the important thing, that this OH should not have to be necessarily a cis diol. That means this should not have to be in the same positions or same directions. Now see the reaction course, the transfers of electrons here, and we will come in detail later. When three or more CH-OH groups are contiguous, the internal ones are obtained as formic acid. So that means if you have consecutive 3 CH-OH group, then this middle one will make formic acid. Per-iodate oxidation of glycerol, for example, gives 2 molar equivalents of formaldehyde and 1 molar equivalent of formic acid. So you have taken this glycerol and you are doing the per-iodate oxidation. So this will give 2 mole of formaldehyde and 1 mole of formic acid. This middle carbon will form the formic acid. Oxidative cleavage also takes place when an hydroxyl group is adjacent to the carbonyl group of an aldehyde or ketone, but not that of an acid or an ester. Glyceraldehyde yields 2 molar equivalents of formic acid and 1 molar equivalent of formaldehyde, while dihydroxyacetone gives 2 molar equivalents of formaldehyde and 1 molar equivalent of carbon dioxide. So you can check that if you take glyceraldehyde, this will form formic acid, another one formic acid, and one formaldehyde molecule. And if you take dihydroxyacetone, this will form one formaldehyde, this one will form carbon dioxide, and the last one will form another one, formaldehyde. Periodic acid does not cleave compounds in which the hydroxyl groups are separated by an intervening CH2 group, nor those in which a hydroxyl group is adjacent to an ether or acetal function. So you can see that here is OH, here is another OH, but periodic acid cannot oxidize this compound because this OH is not on the adjacent carbon. These are being separated by this CH2 group. And in case of this one is the OR, that means OCH3 group, and this one is the OH. So periodic acid cannot oxidize this compound also. Now, mechanisms of periodic acid oxidations. So this is the mechanism of basinal diol. Look at this very carefully. Actually, I have some pain in my throat, that's why I am not describing this all. This is in case of alpha hydroxy carbonyl compound. In case of alpha hydroxy, this hydroxyl group will attack the iodine first, and then this water will be eliminated. Then after that, this OH will attack this carbonyl group, and after that this CC bond will be broken. So finally you will get an acid and an aldehyde. Now in case of 1,2-dicarbonyl compound, this is much more difficult one. At first this OH will attack this carbonyl compound, then this will form OH. At the same time, another one OH will attack this carbonyl group, and this will also form OH. So then the electrons or the bonds will be changed, and this CC bond will be broken. So at last you will get this carboxylic acid and another molecule of carboxylic acid. Two carboxylic acids, but they are not same. If this one is R and this one is R dash, then you will get one R here and another one as R dash. In case of alpha alpha dash, the dihydroxyketone. Okay, this one is the most difficult case. At first, this hydroxyl group will attack the iodine. Then one molecule of water will be eliminated. Then another hydroxyl group will attack the carbonyl. And after that, this OH, that means this carbonyl is forming OH. So this OH will attack another one periodic acid molecule. And after that, this OH, here you can see, after this one, and thereafter this one. So this OH is attacking the iodine. So at last, two bond will be broken. Here one CC bond and another one CC bond. So two simultaneous bond will be broken. So at last you will get aldehyde, another one aldehyde, and this H3I4. The products of the Part-3 reaction may be predicted by replacing each cleaved CC bond with OH groups on the carbons. Water is then removed if needed. So this is the small trick for finding the para-iodate oxidation products. At first, if you see that there is a vicinal diol, just break the carbon-carbon bond. So you are breaking the carbon-carbon bond and then add OH group to each carbon. So at first you are breaking the carbon-carbon bond, then adding OH to both the carbons. And then if you have two hydroxyl groups on the same carbon, then just eliminate 1 mole of water from that. So if you eliminate water, you will get this formaldehyde, and if you eliminate water from this, you will get glyoxylic acid. This one is also similar. In case of this, you have to break these two bonds, because this is an OH, this is keto group, and this is another OH. So all three groups are reactive towards the para-iodate oxidation. So these two carbon bonds will be broken, and then no, what happens? Okay, I was here. So just break these two bonds and then add OH to all of these carbons, and in the middle carbon there will be two OH. In this carbon, two OH groups will be added, and then eliminate water. So you will get this formaldehyde, carbon dioxide, and another one, formaldehyde. So why we are doing this? We can do this because we know that JAM diols are usually unstable and they lose water to form carbonyl compounds. So this is the mechanism of that process. If you have a JAM diol, that means two hydroxyl group on the same carbon, and vicinal diol means two hydroxyl group on two adjacent carbon. So don't be confused with these two terms. Now this hydrogen will give this bond here, and this OH will leave. Actually this OH and this H will make 1 mole of water, 1 molecule of water. How para-iodic acid could be used to distinguish between an aldohexose and a ketohexose. Oxidation of an aldohexose and a ketohexose would each require 5 moles of HiO4, but give different results. An aldohexose yields 5 moles of formic acid and 1 mole of formaldehyde, whereas a ketohexose yields 3 moles of formic acid and 2 moles of formaldehyde and 1 mole of carbon dioxide. So this is the most important thing. In case of ketohexose, you can get 1 mole of carbon dioxide. Therefore, one can distinguish between an aldohexose and a ketohexose by measuring the formic acid and formaldehyde formed, or simply by identifying gaseous carbon dioxide, which gives a white precipitate of calcium carbonate when passed through lime water. So you can easily detect this carbon dioxide, and from that you can say which one is the ketohexose. Para-iodic acid oxidation of glucose. So try this yourself. This is very much simple. Just at first break all these bonds and add OH group, then just eliminate water if possible. And this is the para-iodic acid oxidation of fructose. So that was in case of aldohexose. This is in the case of ketohexose. In case of ketohexose, you are getting 1 molecule of carbon dioxide because of this carbonyl group. How para-iodic acid can be used to distinguish between a 6-membered and a 5-membered glucoside ring. So this is your methyl alpha or beta D glucopyranoside. That means simply methyl glucopyranoside. And if you just oxidize it with para-iodic acid, you will get a dialdehyde. A dialdehyde. That means here and here. These two bonds are being broken, and then you are getting a dialdehyde and formic acid. This middle carbon will form the formic acid. And if you acidify this dialdehyde, you will get this glyceraldehyde, glyoxal and methanol. Methyl glycoside consumes 2 molar equivalents of para-iodic acid and produces 1 molar equivalent of formic acid and 1 molar equivalent of a dialdehyde, which on hydrolysis produces D-glyceraldehyde, glyoxal and methanol. It demonstrates that the glycoside is a 6-membered ring. That is, this glycoside is methyl alpha or beta D glucopyranose. In case of 5-member ring, methyl glucopyranoside, if you do the para-iodic acid oxidation, you will get a trialdehyde and formaldehyde. So there will be this bond will break and this one will break. So you will get a trialdehyde and 1 molecule of formaldehyde. Actually, this one will make the formaldehyde. And then if you hydrolyze this trialdehyde, you will get this and this. For the 5-membered ring, that is a furanose, 2 molar equivalents of para-iodic acid would be required, but 1 molar equivalent of formaldehyde and 1 molar equivalent of a trialdehyde, which on hydrolysis would yield hydroxymelonaldehyde, glyoxal and methanol, would be produced. So by getting these products, by analyzing your products, you can differentiate between a 6-membered ring and a 5-membered ring. Now see this one. You are oxidizing the methyl alpha D glucopyranoside. You are getting this one and this one molecule. This bond and this bond is being broken, but not these two. Okay, these two cannot be oxidized because these two are not a cis diol. Sorry, not cis actually. This OH and this OH are not in the adjacent carbons. They are separated by another one CH2. So this is not a 1,2 glycol. That's why it is not oxidized. And this is in the case of methyl alpha D fructofuranoside. This and this will be broken. Why alpha D glucopyranose is oxidized by HiO4 more rapidly than the beta ionomer at the 1,2 bond. So at the 1,2 bond, the alpha D glucopyranose is oxidized faster by the para-iodic acid. Then what is the reason behind it? Alpha D glucopyranose is the cis 1,2 diol and the beta ionomer is the trans 1,2 diol. So para-iodic acid can oxidize both the cis and trans diol, but as this alpha D glucopyranoside has the cis diol, this will be faster. So since the former can form a cyclic ester with para-iodic acid and the latter cannot, the former is oxidized more rapidly than the latter. So because of this, as these two are in the cis position, one is in the axial and in case of 2, this is in the equatorial. So these cis diols give a faster reaction. Why D-mannose is oxidized faster than beta-D glucose by para-iodic acid? So D-mannose is oxidized faster by the paraodic acid than beta-D-glucose. What is the reason behind it? In the more stable alpha enomer of D-mannopyranose, the OH groups at C2 and C3 are cis to each other. So this OH, C2 and C3, they both are in the up position. This one is the axial up and this one is the equatorial up. So they are in the cis to each other. Whereas in the more stable beta enomer of D-glucopyranose, no two adjacent OH groups are cis to each other. All these OH groups are trans to each other. Look, this one is the equatorial up, this one is the equatorial down, again this one is the equatorial up, this one is the equatorial down. That's why no two hydroxyl groups are cis to each other. Since a cis 1,2-diol can form a cyclic ester with paraodic acid, alpha D-mannopyranose is oxidized more rapidly than beta D-glucopyranose. Paraodic acid works well in aqueous solutions, and lead tetraacetate, that is PbOAc4, gives good result in organic solvents. Since most simple sugars are highly soluble in water, paraodic acid rather than lead tetraacetate is used for their oxidative cleavage. So that's why we use the paraodic acid rather using this lead tetraacetate. Special type of oxidation. Monosaccharide derivatives in which the CH2OH group at C6 has been specifically oxidized to a carbonyl group are called uronic acids. Their names are based on the monosaccharide from which they are derived. For example, specific oxidation of C6 of glucose to a carboxyl group converts glucose to glucuronic acid. In the same way, specific oxidation of C6 of galactose would yield galacturonic acid. This is the form of glucuronic acid and this one is the galacturonic acid. This C6 is being oxidized, whereas this is kept as aldehyde. This is not oxidized, but this one is oxidized. What is the mechanism of it? You have beta D glucopyranose and this one is the alpha D glucofuranose structure. This one not will be the pyranose, this one is the furanose structure. Now you are giving the acetone in HCl or H2SO4 dilute acid medium. So this will form this diisopropyl structure and this third hydroxyl group will be free. Now if you give acetic acid, this will be just converted into the hydroxyl groups, but this will remain same, this portion will remain same. Okay, then you are giving oxygen in platinum and carbon environment, so this can oxidize this CH2OH group into COOH. So in this manner you can specifically oxidize the C6 carbon of aldohexose. Reduction of monosaccharides. Aldoses and ketoses can be reduced with sodium borohydride to compounds called alditols. So you take aldose, add some sodium borohydride or H2PT, that means hydrogen in palladium, in platinum, or even you can take palladium. So you will get alditol, where this CHO group will be converted into CH2OH group. Reduction of D-glucose, for example, it's D-glucitol. So this is your D-glucose and you are reducing it with sodium borohydride, you will get D-glucitol. If you take D-galactose, you will get galactitol, which is also called dulcitol. So this is the dulcitol. Now take beta-D fructopyranose, then this is in equilibrium with its open chain form, and then reduce it with sodium borohydride. You will get both the glucitol and mannitol. That means sodium borohydride basically supplies the hydride ion H minus. So if this H minus attacks from this side, you will get this mannitol, and if this H minus attacks from this side, so this OH will become on the right hand side, so you will get glucitol. Which monosaccharide is reduced to give the same product as that of D-glucose? So you have the the structure of D-glucose, so you know the alditol structure, the glucitol, this one, and you are asked that which other monosaccharide will give the same alditol after being reduced, and the answer is the L-glucose. If you take L-glucose, then if you reduce it, you will get the same alditol. How to get to the answer, I will discuss it later. Oh yeah, I have discussed it here. Easy method to find out. At first, draw the given molecule with Fisher allowed 180-degree rotation. So this is your structure. If this is your glucose, that means here it is said that which monosaccharide is reduced to give the same product as that of D-glucose. So you know the structure of D-glucose. So first draw the D-glucose. Then just rotate it in plane 180-degree rotation. That means this top will come to the bottom and this bottom will go to the top. Just 180-degree in plane rotation. So you will get this, and in the next step just cut it down and replace these two. This CHO group will come here and only this CH2OH group come here. So you will get this structure, which is actually L-glucose. As the former was D, this was D. After rotation, it will convert into L. So this one will become L. This is the L-glucose. Explain why sodium borohydride reduction of D-fructose leads to both D-mannitol and D-glucitol. Reduction of D-fructose creates a new asymmetric carbon atom formed in either of two configurations, and so two diastereomeric products are formed, which I have just told you that this sodium borohydride can attack from this side or can this side. As this is a new asymmetric carbon, it can give two diastereomer, this one and this one. Reduction of aldoses by concentrated HI, that means hydroiodic acid, and red phosphorus. If you take the alpha D glucopyranose, this is the open chain form of D glucose, and then if you give HI red phosphorus, these all OH groups will be converted into hydrogen. So you will get N-hexane. So this one will also be converted into CH3. This CH2OH will also be converted into CH3. A ketohexose cannot be reduced to the corresponding alkane directly by concentrated hydroiodic acid and red phosphorus. However, on successive reduction with sodium amalgam and HI red phosphorus, they form the corresponding alkane. So you cannot use the HI and red phosphorus with the fructopyranose. At first you have to use the sodium amalgam, then you can reduce it with hydroiodic acid and red phosphorus. So you will get the N-hexane. Reactions of monosaccharides with phenyl hydrazine. Osazone formation. This is the structure of phenyl hydrazine. Actually, when I was in class 12, I couldn't understand that why always this nitrogen shows the basic properties or the nucleophilic properties. Why not this one? That's why I have just shared the answer here. This one nitrogen is giving its lone pair to the ring. Actually, this nitrogen has two lone pair. This nitrogen has two lone electrons, okay? And these are actually, this nitrogen is giving this lone pair here inside the ring, and a resonance structure you can get. Again, you can say that this will come here, this will go there, or this will come here, like this. So this lone pair of the nitrogen is involved inside this ring. That's why this nitrogen cannot show the basic property or the nucleophilic activities. This nitrogen is free, there is no conjugation, and it has one lone pair. So this lone pair can show the basic properties. This is your aldose. You are reacting it with phenyl hydrazine and you are getting phenyl hydrazine derivative, which is osazone, phenyl osazone. Osazones are generally yellow crystalline solid. Formation of it results in a loss of chirality center at C2, but does not affect other chirality centers. That's why D-glucose, D-mannose yield the same phenyl osazone. This is the structure of the phenyl osazone in case of D-glucose and D-mannose. As both these two are losing their chirality, that means not two, actually this one is losing its chiral property. That's why the D-mannose and D-glucose both gives same phenyl osazone. Although D-fructose is not an epimer of D-glucose or D-mannose, D-fructose also gives the same osazone, and these three gives the same phenyl osazone. And now come to the mechanism. Oh, this is a larger one. Okay, see this. This is your aldose and this is your phenyl hydrazine. At first the basic nitrogen is attacking here and this bond is being opened. Now what is happening? This nitrogen is losing one proton and forming this. After that again the lone pair of nitrogen attacks here and this OH2 plus leaves. So ultimately you will get this structure, phenyl hydrazone with one condensation, okay. Then actually a rearrangement occurs, which is said Amadori rearrangement. This is the Amadori rearrangement. And after that you will get an imine structure. This another molecule of phenyl hydrazine reacts with this imine, and here this nitrogen will attack here, and in the same kind it will form C double bond N NHPH. And then the third number of molecule of phenyl hydrogen, this one is the third molecule which is involved in the same reaction. This will attack in this carbon and this will here go here. Then after that this proton will be lost, so we will get this, and at last this will go out as ammonia and you will get the final ozone structure. So look at this mechanism very carefully. Ozones of aldohexoses is stabilized by intramolecular hydrogen bonding. Now look at here in case of this portion. Actually this OH is attacking here and forming a ring-like structure, and this double bond is taking a proton, so this is becoming NH and this NH is forming a hydrogen bonding with this nitrogen, with the nitrogen which is attached with the phenyl ring. That means this nitrogen and this proton which is attaching with this nitrogen, they are making a hydrogen bond. So you will get a intramolecular hydrogen bonding. Because of this, the phenyl ozones are stabilized. Now in case of ketose, the same kind of reaction occurs. You just see it yourself. I am not describing this. Just try to understand. Now this mechanism is supported by the observation that when ozone prepared by the reaction of glucose with N15 labeled phenyl hydrazine is treated with ordinary phenyl hydrazine, unlabeled ozone is obtained accompanied by the expulsion of labeled ammonia. So this one is your carbonyl compound and you are giving a labeled phenyl hydrazine. So at first this will form the phenyl hydrazone, and then after the rearrangement the pH NH2 group will leave and you will get this kind of imine structure. Then again another molecule of phenyl hydrazine, unlabeled phenyl hydrazine, will attack here, this one, and form this one, and another molecule of phenyl hydrazine will attack at this carbon, and this NH group will be just expulsed, becoming NH3. So by doing this labeling, by doing this method, scientists have seen that this NH3 bears the labeled nitrogen. That's why they proposed this kind of mechanism. Amadori rearrangement. The Amadori rearrangement was discovered by the organic chemist Mario Amadori. In 1925, he reported this reaction while studying the Maillard reaction. The Maillard reaction he was studying, and then he just invented this rearrangement. The reaction is important in carbohydrate chemistry, specifically the glycation of hemoglobin. The rearrangement is usually preceded by formation of the alpha-hydroxyimine by condensation of an amine with an aldose sugar. The rearrangement itself entails intramolecular redox reaction, converting this alpha-hydroxylamine to an alpha-ketoamine. Now, what is ozone? Removal of the phenyl hydrogen groups in ozones by hydrolyzing these with hydrochloric acid or by treating these with benzaldehyde in the presence of acid yields dicarbonyl compound. These dicarbonyl compounds are known as ozones. So you have this ozone, and if you treat with HCl or just benzaldehyde in acidic medium, you will get a dicarbonyl compound. These dicarbonyl compounds are called ozones. Ozones. Don't say it ozone, okay? Ozone is the O3 is the ozone, and this is the ozone. How to convert an aldose to a 2-ketose by the oxygen formation. By this you can just convert an aldose to a 2-ketose, that means you can just convert the glucose to fructose by this manner. So at first make the phenyl hydrazone, that means oxazone, at first from the oxazone, then treat it with benzaldehyde in the acidic medium. So these phenyl hydrogen groups will be removed, and you will get the dicarbonyl compound, which is ozone, which is ozone, and just treat it with zinc and acetic acid. So if you treat it with zinc and acetic acid, this will just reduce this aldehyde group, not this carbonyl group. And after reducing this aldehyde group, you will get 2-ketose. By this procedure, glucose can be converted into fructose. I'm very much tired now, but let's go to the next slide. Killiany-Fischer synthesis. The Killiany-Fischer synthesis, named for German chemist Heinrich Killiany and Hermann Emil Fischer, is a method for synthesizing monosaccharides. In this procedure, we can increase the chain length by adding one carbon atom to the aldehyde end of the aldose. It can be described by the synthesis of D-threose and D-erythrose from D-glyceraldehyde. Addition of hydrogen cyanide to glyceraldehyde produces 2 epimeric cyanohydrins. Because the reaction creates a new chirality center, the cyanohydrins can be separated easily since they are diastereomers, and each can be converted to an aldose through hydrolysis. Acidification, lactonization, and reduction with sodium amalgam at pH 3 to 5. One cyanohydrin ultimately yields D-erythrose and the other yields D-threose. Now let's see this. You have got, I am just zooming this, okay. You have this glyceraldehyde. This one is your glyceraldehyde. And if you add HCN, you will get 2 types of cyanohydrin, which are epimeric, because this OH is in the right here and this OH is in the left here. So the difference is only about that. Now just react the BaOH whole twice in the acidic medium, that means baryta. You are reacting with barium hydroxide. Then these cyanohydrins, that means these CN groups, will be converted into COOH, carboxylic acid groups. Now these carboxylic acids, this OH will just attack here and will form a gamma aldenolactone. Similarly, this OH will also attack here and they will form this gamma aldenolactones. And if you just react with sodium amalgam at pH 3 to 5, then this lactone will be converted into aldehyde group, and ultimately you will get erythrose and threose. Okay. The mixture of cyanohydrins can also be converted into a mixture of aldoses by catalytic hydrogenation, and these aldoses can be separated. Nowadays, the technique is applied for synthesis. That means this technique, this catalytic hydrogenation. Okay, let me zoom in. This is the procedure of the catalytic hydrogenation. You have this CN, and then if you give some catalyst and control the pH of the reaction, you will get this imine intermediate CH double bond NH, and then add hydrolysis. This after doing the hydrolysis, you will get aldehyde. Now this is your D-arabinose. This one is the D-arabinose. If you add the HCN and KCN, this will just step up. This is just a step up reaction. This CHO will give this CHOH, and CN will be added. Then you can get this one and this one. After that, if you add D2 instead of H2, that means instead of hydrogen, if you add deuterium, then this will become CDO, and in ultimate case this will become the CDO instead of CHO, 1-deuterio D-glucose. Wolfram method. In case of Wolfram method, D-fructose can be prepared from D-arabinose. Just start with the arabinose and then add bromine water. This aldehyde group will be oxidized into carboxylic acid, and then you are adding this acetic anhydride and dichloroSOCl2, that means sulfuryl chloride. I'm confused whether it is said sulfuryl chloride or not. Okay, just leave it. Then you will get this structure where this OH will be converted into OAC, and this COOH group will be converted into COCl. Then add diazomethane CH2N2. Then you will get this. Here actually diazomethane is reacting as this is actually a SN2 reaction. This CH2 is in the minus state, so this can attack this carbonyl and this chlorine will leave. So you are getting this. If you treat it with barium hydroxide and acetic acid, at first acetic acid, then if you give barium hydroxide, you will get D-fructose. Okay, yes, this is the structure of diazomethane. I have shown the structure. Here in this canonical form, this CH2 is in the minus state, CH2 minus and N2 plus. Actually this is the nucleophile, CH2 minus. This will attack the carbonyl. Rough degradation. In 1898, Otto Ruff published his work on the transformation of D-glucose to D-arabinose, which is called the Ruff degradation. Ruff degradation involves oxidation of the aldose to an aldonic acid using bromine water, and then oxidative decarboxylation of the aldonic acid to the next lower aldose using hydrogen peroxide and ferric sulfate. So what he has done, he took the D-ribose and just converting it to the D-ribonic acid by treating it with bromine water. So this CHO group is converted into COOH group. Then he has used that hydrogen peroxide and ferric sulfate, Fe2SO4 whole 3. So he got the structure of D-erythrose. And don't be confused with the Fenton reagent. Fenton reagent is the hydrogen peroxide and the ferrous sulfate. That's not the ferric sulfate, okay? Fenton reagent is the mixture of hydrogen peroxide and ferrous sulfate. But in case of rough degradation, he has used ferric sulfate. So this is the structure of your D-glucose. Then treat with bromine water. You will get aldonic acid, and then this aldonic acid actually is converted to a calcium salt. So you take calcium carbonate, you will get this calcium salt. Then after this, just treat it with H2O2 and FeOAC whole thrice or Fe2SO4 whole 3. Then you will get araminose. So in case of rough degradation, you can use both this way. The one which Rough has used, and this one is the modified one. Now see the mechanism of oxidative decarboxylation. At first, this hydrogen peroxide is being cleaved. This bond will cleave as an homolytic cleavage. So two hydroxyl group will be prepared. And what will happen? This O minus will give its, okay, just let me draw it. This O minus will give its electron to this OH radical, and this OH will become OH minus. So by losing the electron, this O minus will be converted into oxygen radical. Actually here is the oxidation occurring. This O minus is becoming the O radical, and after that this radical will come here. This bond will also be cleaved. That means here will also occur a homolytic cleavage, and after that you will get this carbon radical, this one carbon radical, and this OH group will also be cleaved now. Now another one OH radical will come here and take up this hydrogen as hydrogen radical. So this oxygen will also form a radical. Now this carbon and oxygen radical will form a bond. So this is the actual reaction mechanism. Now read this. Use of H2O2 and Fe2SO4 whole 3 is often called rough Fenton degradation. In case of Fenton degradation, that was ferrous sulfate, but as it is ferric sulfate, not the ferrous sulfate, this is called rough Fenton degradation. This is the entire family tree of the aldohexose. If you start with any one of these 8 pair, this 8, at last you will get the glyceraldehyde if you just go on doing the rough degradation. If you take any one of aldohexose, you will get the corresponding aldopentose after one rough degradation. After another rough degradation, you will get the corresponding aldotetrose, and then after another rough degradation, you will get the aldotriose, which is the glyceraldehyde. Whole degradation. This is the structure of your glucose, and in case of whole degradation, you are treating it with hydroxylamine and this sodium methoxide. So what will happen? This hydroxylamine, this NH2 group will condense with this carbonyl group. So you will get this imine structure. And then if you treat with acetic anhydride in sodium acetate and acetic acid mixture, then you will get OAC here. This OH will be converted into OAC, and this C double bond NOH will be converted into CN. Then treat it with sodium methoxide in the methanol, then you will get an aldehyde. But this is actually a lower one, because this carbon is forming the aldehyde here. This is actually almost similar to the rough degradation, but the process is a little bit different, and here the hydroxylamine is being used. So you are converting a aldohexose to a aldopentose by whole degradation. Now this is the detailed mechanism of the transesterification. What is the transesterification? The transesterification means, assume that you have one ester and you are reacting it with another alcohol, then you will get the corresponding ester. So from one ester you are getting another one ester. This is called transesterification. Now this is the mechanism of the whole degradation. In case of this whole degradation, one process involves the transesterification. Just watch it carefully. The OMe group is attacking here. This bond is being opened. Then what is happening? This O minus is coming back. Then this bond is being broken. Ultimately this group is being removed. So ultimately this group is being removed, and this O minus is taking a proton here. So you are getting CHOHCN. And after that this hydrogen also leaves by taking this cyanide as HCN, and you will get a lower aldehyde. This, if it has n number of carbon atoms, this will have n-1 carbon atoms. Wiedemann degradation. Wiedemann degradation is named after Rudolf Adrian Wiedemann, who discovered it in 1910. The reaction is used for the degradation of alpha hydroxylamide. It proceeds very slowly at room temperature. Therefore, the reaction mixture is heated up to 60 to 65 degrees centigrade. This is the general reaction scheme of Wiedemann degradation. Just watch it. This is your alpha hydroxylamide. This is the amide group CONH2, and in the alpha carbon there is a hydroxyl group. That's why this is a alpha hydroxylamide. And just treat it with NaOCl. NaOCl means the combination of NaOH and Cl2. This will form the NaOCl. So you will get this aldehyde, RCHO. The first step of Wiedemann degradation involves oxidation of the aldose with bromine water, followed by acidification to yield a lactone. The lactone is then heated with ammonia to give an amide. This alpha hydroxyamide is finally treated with Cl2 and NaOH to give a new lower carbon sugar. This will be alpha, okay, not A. The reaction mechanism is related with Hofmann degradation. So just see the reaction mechanism here. At first you are treating with bromine water and then acidifying. So you are getting a gamma lactone, and then heating with ammonia. So you are getting an amide CONH2 amide, and then you are treating with NaOCl, that means the NaOH plus Cl2. Then you will get an isocyanate which will form D-arabinose, that means which has one carbon less than this one. Okay, this is the reaction mechanism of alpha hydroxyamide. At first this base will take up this proton, and this NH will become minus, then this NH minus will take one chlorine and become CONHCl, then another one OH minus. What it will do? Okay, it will take this hydrogen. This OH minus will take this hydrogen from this nitrogen, and this nitrogen will become minus. Now this will give electron here, and this carbon-carbon bond will be broken, and this bond will be transferred to the nitrogen. So this structure will form after rearrangement. Then this OH minus will take up this proton, and this bond is going here, and this one will be free. So you are getting finally an aldose. If there is no free hydroxyl group on the alpha carbon atom, that is, the atom is attached to a methoxy group, then treatment with alkaline sodium hypochlorite produces an aldehyde, methanol, ammonia and carbon dioxide. That means there is no free hydroxyl group on the alpha carbon atom. This is the alpha carbon and there is no free hydroxyl group. So now if you just try to do the Wienemann degradation, you will get the aldehyde and this methanol, ammonia and carbon dioxide. Wienemann degradation could also be executed with alpha-beta unsaturated carbonic acid amides. For example, it can be done in acrylamide. So if you are interested, you can see this mechanism also. I am not going in details because this is not necessary in this stage in case of carbohydrate chemistry, but if you are interested in this kind of mechanisms, you can see it. Fischer's proof of the configuration of D-glucose. Step 1. Since an aldohexose has 4 chirality centers, in total 2 to the power 4, that means 16 stereoisomers are possible, one of which is the glucose. Fischer arbitrarily decided to limit his attention to the 8 structures with the D configuration of the highest asymmetric carbon. So at first Fischer decided that this highest asymmetric carbon have D configuration. This carbon has the D configuration. Fischer arbitrarily chose that. Now step 2. Arabinose and aldopentose is converted into both glucose and mannose by a Killiany-Fischer synthesis. So Fischer saw that arabinose can be converted into both glucose and mannose by Killiany-Fischer synthesis. From this observation, Fischer deduced that glucose and mannose are epimeric at carbon 2, and that the configuration of arabinose at carbons 2, 3 and 4 is the same as that of glucose and mannose at carbon 3, 4 and 5 respectively. So this configuration of 2, 3 and 4 will be same for the configuration of 3, 4 and 5 in glucose and mannose. Fischer understood that. He was just a genius person. Now step 3. Arabinose can be oxidized by dilute nitric acid to an optically active alderic acid. From this observation, Fisher concluded that the OH group at carbon 2 of arabinos must be on the left. If this OH group were on the right, then the alderic acid of arabinos would have to be meso, and thus optically inactive, regardless of the configuration of the OH group at carbon 3. So what he saw that the experiment shows that if you oxidize the arabinos, you are getting an optically active compound. So Fisher understood that this one OH is in the right, so this OH must be in the left, because if you oxidize this CH2OH, and this CHO group will be converted into COOH. Now this OH, if these OH are in the same side, then you will get a meso compound, because this is the plane of the symmetry. That's why you will get a meso compound. But in actual case, you are getting an optically active compound. So Fisher understood that this OH is in the right and this OH is in the left side. Step 4. Oxidations of both glucose and mannose with HNO3 give optically active alderic acids. From this observation, Fisher deduced that the OH group at carbon 4 is on the right in both glucose and mannose. So what he has done, he has just oxidized both glucose and mannose. So if you just, one of this is glucose and one of this is mannose. He didn't know at first that which one is the glucose and which one is the mannose, but after oxidation he got that both are optically active. So he understood that this 3 position, this 3 OH, not 3 actually, this one is the 4th carbon, this one is the attached with the 4th carbon. This OH group is on the right hand side, because if it were in the left hand side, then in case of the oxidation, this will become a meso compound. So the glucose and mannose, both of them cannot give optically active compound. In this case, if the OHs were on the left, then one will be optically active, another one will not be optically active. But the experiment shows that both of them are optically active. So from this, Fisher deduced that this OH is on the right. Now step 5. This one was legendary. Fisher had already developed a method for effectively interchanging the two end groups, that means the aldehyde and the primary alcohol of an aldose chain. And with brilliant logic, Fisher realized that glucose will give a new aldohexose due to an interchange of the end groups, while mannose would yield the same aldohexose. So let me just zoom in. So this is your mannose, because if you just interconvert this CH2OH and this CHO group, if you just change these two groups, then you will get the same structure, that means same molecule. But in case of this glucose, if you change this CH2OH and CHO group, after interchange you will get a different form, different structure, which is actually L-glucose. But in case of mannose, both were same before and after exchange of this CH2OH and CHO group. By this logic, Fisher understood that which one is the structure of glucose and which one is the structure of mannose. The procedure Fisher used for interchanging the ends of the glucose chain began with one of the gamma lactones of D-glucaric acid. So at first he took this gamma lactone, Then he reduced it with the sodium amalgam. So this is becoming the CH2OH, and then this is again forming a gamma aldenolactone. This OH is forming with this carbonyl group. So if he reduced this also with sodium amalgam at pH 3 to 5, so this one is also forming the aldehyde group. And at last he got the L-glucose structure from the glucose. The second reduction with sodium amalgam is carried out at pH 3 to 5. Under this condition, reduction of the lactone yields an aldehyde and not a primary alcohol. So this is very much important to control this pH of the reaction. Now come to deoxy sugar. Monosaccharides in which an OH group has been replaced by hydrogen are known as deoxy sugars. The most important deoxy sugar, because it occurs in DNA, is deoxyribose. Other deoxy sugars that occur widely in polysaccharides are L-rhamnose and L-fucose. This is the 2-deoxyribose. This OH is absent because there is only H here. This is the structure of L-rhamnose. This one is the L-fucose. Now come to deoxyribose. Deoxyribose was discovered in 1929 by Phobos Levin. Its name indicates that it is a deoxy sugar, meaning that it is derived from the sugar ribose by loss of an oxygen atom. Since the pentose sugars, arabinose and ribose, only differ by the stereochemistry at C2, so 2-deoxyribose and 2-deoxyarabinose are equivalent, although the latter term is rarely used because ribose is the precursor to deoxyribose. This is the structure of your ribose, and this one is the deoxyribose. This OH is changed by only hydrogen. In aqueous solution, deoxyribose primarily exists as a mixture of three structures. In aqueous solution, a deoxyribose exists like this with a three structure. This one is the open chain structure, this one is the deoxyribofuranose, and this one is the deoxyribopyranose. In RNA you will get the ribose, in DNA you will get deoxyribose, and there is a convenience of this deoxyribose in DNA. The absence of the 2-hydroxyl group in deoxyribose is apparently responsible for the increased mechanical flexibility of DNA compared to RNA. So because of the absence of the hydroxyl group, the DNA is more mechanically flexible, which allows it to adopt the double helix conformation, whereas RNA is single-stranded. So because of this, DNA gets the double helix conformation. Barton deoxygenation. The Barton-McCombie deoxygenation is an organic reaction in which a hydroxy functional group is a hydroxy functional group in an organic compound is replaced by a hydrogen to give an alkyl group. It is named after British chemist Sir Derek Harold Richard Barton, large name, and Stuart W. McCombie. This deoxygenation reaction is a radical substitution. I have shown this mechanism here. At first take an alcohol and treat it with a base. So the base will take up this proton and then you will get alkoxide ion. This alkoxide will attack this carbon disulfide CS2 and will form this structure. This sulfur anion will take up a methyl group from the methyl iodide and ultimately it will form a xanthate. Now come to the structure of AIBN, that means azo base isobutylonitrile. This is the structure of AIBN and this is the radical initiator. Let me zoom in. This is actually the radical initiator. This bond this bond and this bond goes through a homolytic cleavage. That means this and this. These two bonds goes through a homolytic cleavage, thus a radical is formed. This one radical. This is the 2-cyanoprop-2-yle radical. And this will form nitrogen. After that, this radical will take a proton from this Bu3SNH. I have to zoom this. And then this Bu3SN radical will attack this sulfur. And this bond will be opened and this carbon will become a radical now. Now after that, this radical will go here and this bond will be broken. So ultimately an alkyl radical will be formed. And this alkyl radical will snatch a hydrogen from Bu3SNH and ultimately it will make an alkane from an alcohol. The reaction mechanism consists of a catalytic radical initiation step and a propagation step. The alcohol is first converted into a reactive thionoester or xanthate. Heating of AIBN results in its homolytic cleavage, generating two 2-cyanoprop-2-yle radicals which abstract a proton from tributylstannone to generate tributylstanyl radicals. The tributyl-tene radical attacks the xanthate group at the sulfur atom, which leads to a homolytic cleavage of the CS pi bond. This leaves a carbon-centered radical that forms a CO pi bond through homolytic cleavage of the RO sigma bond, giving rise to an alkyl radical. The sulfur-tene bond in this compound is very stable and provides the driving force of this reaction. The alkyl radical then abstracts a hydrogen atom from another molecule of tributylstannone, generating the desired deoxygenated product. Now a new radical species is ready for propagation of the reaction. This is another mechanism which I have shown. If you wish, you can just do this yourself. First take this glucose, then react it with acetic anhydride, then you will get pentacetate, and then react it with HBr. React it with HBr. Then this bromine will take the axial position, and then from this, if you give zinc, this zinc will snatch this bromine and form a glycol. After that, I think I have missed something. Okay, I have I have missed this OAC groups. OAC and OAC will be here. This will form a glycal. And if you react the tributyl stannone here and this double bond CN, if you react here with this, then you will get actually this one. Now I am telling you the mechanism. At first this radical will snatch a hydrogen from this. This will snatch a hydrogen. Then this will become a radical. Then this radical will attack the bromine. After that the bromine will give its electron here. Actually this bonded electron, one electron will be taken by bromine, another one will be taken by this carbon. So a radical, carbon radical will form, and this radical actually attacks here, and then this species will be formed, and at last this will snatch a proton from this, and ultimately the product will be formed. Now just this is an important note about glycals. What is glycal? Actually glycals are sugar derivatives which have a pyranose ring structure and a double bond between C1 and C2. For example, D-glucal. Glycals may be prepared by reducing acetobromo compounds with zinc dust and acetic acid. So this is the form of glycal, where this C1 and C2 carbons are attached with a double bond. Okay, so finish.